Okay, let's solve another problem from section 4.4, dealing with local extrema, concavity, and points of inflection. What I want to do is go ahead and open up my iPad and solve the problem from there. So the problem is that you're given this function, this cubic function, and we're asked to find the local extrema, whether it's concave up, and where it's concave up and concave down, and any points of inflection that may occur, see if there are any. All right, so I'm recognizing in this situation when I read that, local extrema, that's indicating we can use the first derivative test to find local extrema or the second derivative test to find local extrema. That's the goal of both of those tests. So the only thing I'm being asked to do is concave up and concave down and points of inflection. So I could use the second derivative test to only and not worry about the first derivative test. I do need to find the points of concern, the critical points, but at the same time, second derivative test is all I'm going to need. So that's what I'll do in this problem. So let's first take the first derivative and see where we're going from here. First derivative is equal to 6x squared minus 12x plus 6. All right, let's factor that out. There's a 6 common. That gives me x squared minus 2x plus 1. And now I can see that can be factored down. It's got to be x, and it's got to be 1 and 1 if it's an integer result, and that's got to be minus and minus. So this turns out to be the perfect squared situation. So there is only one critical point, critical value in this situation. So when I'm setting this equal to 0, there's only one to be concerned about, and that is at x minus 1 equals 0, excuse me. So I have x minus 1 equals 0. So that occurs at x equals 1. There's only one critical point at x equals 1. So if I go now to the second derivative test, that's where we'll plug in the critical value into that and see if it's concave up or concave down. That's what the idea is. So one of the situations is that we need to take the second derivative. First derivative is here. So I take the second derivative. The derivative of that gives me 12x minus 12. 12 is common, so I get x minus 1. So with the second derivative now, remember that if I take the point of concern, which is the critical point, and plug it into the original function, to the second derivative function, excuse me, that will determine whether it's concave up or concave down, if the result is positive or negative. So if I go and plug what it's def double prime of the critical value we have, we get 12 minus 12, which is 12 minus 12, which is 0. Now the second derivative test says that if I plug in the critical value and critical point and I get a positive outcome, then that indicates positive up, concave up. And if I plug in the critical value and get a negative value, that's concave down. Well, I get 0. That's indicating that that's actually setting it up to say that that is a possible point of inflection. So the whole thing we've got to do is check to the right and to the left of the critical point, which is 1. Check to the left and to the right. So if I check at 0 and check at 2, I can determine whether, if it changes from negative to positive or positive to negative, the concavity, then that'll indicate that x equals 1 is a point of inflection. So I plug in 0 to the second derivative, and I get 0 minus 12, which is negative 12, which is negative. All right, so I get a negative on this side, which means it's down like this, right? And if I plug in 2 over here, then I get at the second derivative, I get 12 times 2 minus 12 is 24 minus 12, which is positive 12. So that gives me a positive value. That means it's concave up over here. And that means since it goes from concave down to concave up, that this must be a point of inflection at x equals 1. Okay, so The first question is, are there any local extrema? Well, the second derivative test tells us we plugged in the critical point, we didn't get a plus or a minus, we got 0. So there are no local extrema. So A, no local max, no local min, no local extrema. B, concave up or concave down intervals. So let's check that out. If we go, we see that 1 is a point of inflection, so the far right is 1 and it goes down to negative infinity to the left here. So concave down on the interval negative infinity to 1, and concave up on interval 1 to infinity. Okay, and we verify the point of inflection is at x equals 1. Let's calculate what the y is in that situation. So we have to go back to the original function now. If we're trying to get the y coordinate, when we need f of 1. And plugging 1 is pretty straightforward. We get 2 minus 6 plus 6 minus 3. The 6 is canceled. We end up with 2 minus 3, and that's minus 1. So we have the point 1, negative 1. So the point of inflection, can I fit it in there? Yeah. Point of inflection is at 1, negative 1. Okay? So that is, we just used the second derivative test in that situation and got those 3 answers. So what does that graph look like if it's got no point of inflection? I mean, it's got a point of inflection, but there's no extrema. There's no local extrema. There's no local max, local min. What does that look like? So let's take a look at what we're talking about here. I want to go to Desmos, right? So if I want to go to Desmos, I get what the graph looks like. And that turns out to be, yes, that's what it looks like. So you can see that the situation is that that is new share. Okay, here we go. Now I think now you'll be able to see it. Yes. Okay, so now you can see what the graph looks like. No local min, no local max. The graph, it doesn't dip, you know, it doesn't go up and come back down or that type of thing. So at 1, it shifts over at a point of inflection, and to the right, it's concave up, and to the left, it's concave down. So there is no local max or local min. That's what the graph looks like. So that's a situation of another circumstance that can possibly happen when you're solving these problems, all right? That's it. That's another problem from section 4.4. Be well. Ask me if you've got any questions. Get with me during my office hours.